All right, so let's work this problem. We've already done one. Let's see what's the difference here. Well, the first question you have to ask yourself is: this is a continuous? Can you write a continuous moment for this problem?
Yes.
Sure, you can. It'll be a little more complicated than we did before, but we can do that. So let's start with that process. So just like we did before, we'll assume we have a cut, and you have to decide whether you want to work, say, the left side or the right side. Now, unlike the previous problem, I think there's a clear choice here. If you go left, you're going to be working with a triangular distributed load, probably as a function of x. Not probably, as a function of x. If you choose to do the right-hand side, well, it still will be a function of x. It'll just be a little more complicated, and of course it'll be trapezoidal, and that's just a lot more to keep up with. So I think you should definitely go to the left. And when you do that, we're going to need the reaction at A. So just like we did before, let's draw a free body diagram of the structure. I'll assume a direction for AY and BY, and then we'll find the concentrated equivalent of this distributed load, which is a triangle. So that's 1/2 base, which is L, times height, which is W. So now the total load here is WL over 2. And where is it located? Well, the centroid of a triangle is about 1/3 the distance from the larger end. So in our case, that would be L over 3, and then the remaining part would be 2L over 3. So that's everything we need. To find AY, we will sum moments at B and set it equal to 0. So about B, my concentrated equivalent load creates what kind of moment? Positive or negative? Positive. So the force is WL over 2 times a moment arm of L over 3. And then AY will create negative moment. And that'll be AY times L. So it looks like AY will be WL over 6. And that seems reasonable. So basically, 1/3 of this load goes to AY, and 2/3 of it would go to BY. Okay, now that we've determined that, let's cut our structure at some distance x. We know our reaction at AY is WL over 6. At the cut, we have a shear force and a bending moment. And now we need to resolve this triangular load here. We've already talked about it. We know that it's 1/2 base times height. So 1/2 base x times height. Ooh, what's the height? Yeah, so what's the slope? What's the slope of this line?
W over L.
Yeah, it rises W for a run of L, so it's WL. So this at any point we want would be what? It would be WX over L. Right? When x is 0, you get 0. When x is equal to L, the L's cancel and you get W. So now the force, I'll write this off this side here. So the force will be 1/2 the base, which is x, times the height, which is WX over L. And you run that through, you get WX squared over 2L. Of course, if you put in x equal to L, right, you get WL squared over 2L, you get WL over 2, which is the same thing we got before when we did the whole structure. So that seems to match. And then what's the distance from the cut? Well, it'll be 1/3 of the distance. The distance is x, so that'll be x over 3. Just want to give you a little bit more data on that. So now we'll come over here and we will some moments at our cut. Make sure we're in equilibrium. So looking at our free body diagram, start here on the right. The moment is positive. The moment due to the concentrated equivalent force is positive. So the force was Wx squared over 2L, and the distance d was x over 3. That's that part. And then we have the reaction force, which is WL over 6, and that has a moment arm of x, and that creates negative moment. WL over 6 is the force, and x is the moment arm. So you just take your time. You can write an equation for the moment. Let's see. This is Wx cubed over 6L, and that's negative. So negative Wx cubed over 6L, and this becomes WLx over 6. Does it work? Where do we know the moment in this structure?
0.
At x equals 0, the moment should be 0 because it's a pin. So let's see. So the moment at x equals 0 should be 0. And if you put an x equals 0, what do you know? You get 0. At the other end, where x is equal to L, is a pin. That should also be 0 moment. You put in L here, you get negative WL squared over 6 plus WL squared over 6. That's 0. So that seems to be okay. Both of those seem to work. So our first step is to integrate the moment divided by EI. It looks like I've got a common W over 6, so I'll factor that out. Maybe I'll factor out the L too. So what do I get? I'll get W... What? I can do anything I want. If I factor this L out, this will become L squared. That's all. All right? You don't want to? Okay, I won't do it. You don't like it. That's okay. I want to do what you guys want. I aim to please. So what we're left with is L cubed over, x squared over L, x cubed over L, and that's a negative, plus XL over, that's just it, XL. There's no 6. I took the 6 out. And we're going to do that dx. So we get our W over 6EI. It's a constant. What have I got left? I've got minus x to the 4th over 4L plus x squared L over 2. Oops, sorry, I'm running into stuff here. C1. Make a little border there. Is that okay? Do we know anything about slope in this structure? Well, I know somewhere in here it's going to be 0, but I don't know where. So I just got to not worry about that. But I'm okay because I do have 1 and 2 conditions for displacement. So let's just continue on. We know the displacement is going to be the integral of the slope. So I'm going to take all that and integrate it. So again, I'll get my W over 6EI as a constant to these terms. So I got x to the 5th over 20L plus LX cubed over 6 plus C1 integrated is C1x, and then I get an integration constant C2. What?
There's a duck in the room somewhere.
There's a duck in the room?
Yeah.
A flying duck.
Ah. Early morning visit to the pod. What do we do now?
Check. Oh, no,
Yeah, so usually the one at x equals 0 is a good place to start, so I'll do that. So when I plug in x equals 0, I should get a displacement of 0. And you plug in x equals 0, that term goes away, that term goes away, that term goes away. You're left with C2. That's good. One down, one to go. The next one I have to deal with is we know that at x equal L, which is support B, the displacement is also 0. So let's plug in x equal L here and see what we get. So I've got 6EI, that's a constant. Let's see what we've got here. I got L to the 4th over 20 plus L to the 4th over 6. The only common denominator I can think of is 60. So this would be 3/60ths negative plus 10/60ths positive. That gives me positive 7/60ths. Did you buy that? Is that okay? Check that out. What's that? Yeah, I haven't got to that part yet. I'm just doing this part.
Cool.
Yeah. Then plus C1L. So all I have to do is solve for C1. So it looks like C1 is going to be all this divided by L and negative. So that's going to be minus W over 6EI. And this term here divided by L will be 7L cubed over 60. Now for me, technically you're done because you've solved the problem. You now have an equation for displacement because I've solved for C1 and C2. You can see if you stick this C1 back in here, it's kind of a polynomial mess. And if you took your time, you could wiggle it around and find some common denominators. We've already know this is 60, so times 6, there's going to probably be a 360 out here in the denominator. And you could probably work it around. But that's good enough for me. Yeah.
What's the power difference?
Because it's going to be multiplied by x. So ultimately, every term in this problem will have x to the 4th or L to the 4th as a dimension. This is L to the 5th, but it's divided by L, so that's linked to the 4th. This is linked and cubed, that's to the 4th. C1 is cubed, and then another L will be to the 4th. So they all have the same dimensions. Okay, cool. I guess you should check it to make sure it works. I mean, obviously, if I put in x equal to 0, the whole thing goes to 0. What if I put in x equal to L? Well, I've already checked that here, so hopefully that would work too. Where's the maximum displacement? Well, remember, you would have to go up here to your slope equation, which is now a quartic equation, and find the roots of a quartic. It's not as crazy as it might seem, but it is possible. I just happen to know that the answer is somewhere about like 0.55 L, somewhere in that range, just a little to the right of the center. And once you found that root, remember there's technically 4 roots here. Once you would find the one that's between 0 and L, you take that value and plug it in here, you find the maximum displacement.
Question. So if your slope equation, is that giving you the slope in radians?
Yes.
Okay.
It's dimensionless. If you looked at the dimensions of all that, you would come up with no dimension. Hopefully, when you look at the dimensions of this, you can come up with length. Hopefully. Any questions about that? All right. So this is the perfect method, right? We should use this for every problem we encounter, right?
I don't think so.
Can we use it for any problem we encounter? I say yes, we can. Would it be the most efficient path to the solution?